Hello, class. We are going to learn about calculus theorems. There are 4 of them that we're going to talk about today. We're just going to look at one example of each, just so that you guys have an idea of all the theorems that they have in calculus. Well, 4 of the major ones anyway. So on page 107, you can read about the intermediate value theorem, but it is shortened to be IVT, okay? If f of x is continuous on a closed interval from a to b. So it has to be continuous on a closed interval for a to b. And f of a is not equal to f of b, then all the y values between f of a and f of b must be obtained between a and b. And I know, like, what? What is that talking about? We're going to look at a picture. I'll show you what it means. So, if f of x is continuous on a closed interval, so it has to be continuous, can't be broken, can't have a jump, discontinuity, can't have a hole, has to be continuous. You have a is equal to b. No, you have a and b. Those are just x values. F of a is not equal to f of b. Then all the y values between f of a and f of b must be obtained between that a and b point. So let's look at our picture. Super easy to understand when you're looking at a picture. We'll call this A and we'll call this B. And let's say I tell you that f of A is equal to 4 and f of B is equal to 8. So f of A is equal to 4 and f of B is equal to 8. Okay? Now, what they're then saying is, all of these y values have to be available or used in your x values between a and b. Because there's no way for you to skip y is equal to 5, 6, 7, or any of those intervals in between to get from this point to this point if you're continuous. Now, you can go lots of ways to get there. You can go down and you can pretend like you're not going to get there, but in order to get here, you still have to use these y values. So it's not like you have to go there directly, but eventually, some point in here has to have the y value of 5. Some x value in here has to have the y value of 6. Some point in here has to have the y value of 7, and so forth. That's called the intermediate value theorem, meaning if you've got 2 points, A and B, and they have 2 different y values, a y value must occur at each of those points in between those 2 y values. Okay? Now, how's that used? What does that look like? All right, so let's look at our example here. It says, use the intermediate value theorem, IVT, to show that f of x equaling x cubed plus x takes on the value of 9 for some value x in 1 to 2. So your distance is from 1 to 2. All right, so let's take a look at our graph as well. Here's 1, here's 2. Well, we need to know our y values. What is f of 1? What is f of 2? What are their y values? Well, to find f of 1, you plug 1 into your equation, and we find out that f of 1 is equal to 2. Okay, so the point 1 is right here at 2. So then it says, well, f of 2, okay, well, 2 cubed plus 1. So 2 cubed is 8. Oh, sorry, x. This will be a 2. 2 cubed plus 2. 2 cubed is 8 plus 2 is equal to 10. So f of 2 is equal to 10. Now, IVT, excuse me, I just ate some chips. One was kind of cut in my throat. IVT says that every y value has to exist between y equals 2 and y equals 10 if you're using an x value in between 1 and 2, which means 9 must occur because 9 is in between 2 and 10. Okay? So, because f of 1 equals 2 and f of 2 equals 10, and the intermediate value theorem, 9 must be a value between 1 and 2. Now, do we know what x value? No, we don't know what x value, although as we're getting closer, it's going to be something that's close to 2. So maybe 1.8, 1.9, something like that. Well, we could put it into Desmos to figure it out. But at this point, we don't care what that value is. We just care that it exists. Now, does this show up a ton? Not necessarily. It's not really going to show up a ton on a free response. They might say something like this: use the intermediate value to show. And they ask that, you're just showing what you already know. You have to plug in the 1 and plug in the 2 and make sure that this value is in between. Now, could you use IVT to show that 11 is a value? And the answer would be no, because 11 isn't in between 2 and 10. So it wouldn't work for that one. All right, extreme value theorem. Now notice extreme value theorem starts off just like intermediate. Extreme value theorem, EVT, is if f of x is continuous on a closed interval a to b. We say, then there exists a max and min point. And this max and min point, we're talking about our absolute. There has to be an absolute max or a min. So extreme value theorem is just talking about absolute max and min, which we learned last chapter. So we can even look at a graph of this one too. What's nice with these videos is if it takes you a little bit longer to draw the graph, you can hit pause and then hit start when your graph is drawn. So let's say I have this picture and I go here and then I go down there and then I go up here and then I go right here. Okay? Boom, boom. Right here, that is our absolute min. And right here, that is our absolute max. You're just looking at the very top of the graph and the very bottom of the graph. Now remember, absolute maxes and mins occur at relative maxes and mins, so critical points, or end points. So we're going to do this example, this EVT example, find the max and the min for y equals this equation from -2 to 2. But guess what? This was on the very last test. So it's the exact same thing. We're just giving it a cool theorem name. Okay? So instead of saying find the max and the min, we're saying use EVT. Cool theorem name. Now, you can find all this information on page 218 if you want to take a look at it in your book. But let's take a look at what we had to do. When we were finding the max and the min, you wanted to evaluate your function at -2 and your function at 2, because these were the endpoints. Now, we also needed to evaluate our function at our critical points. We just don't know what our critical points are or how many of them there are. So we got to find our critical points first. Well, the critical points you found by doing the derivative and setting it equal to 0. Now we're factoring this, and however you learn to factor, please do so. So if you did the little table and you factored by grouping, do the little table and factor by grouping. If you're a circle, slide, divide person, circle, slide, divide. I don't care how you factor as long as you factor correctly. I'm a circle, slide, divide person, even though some of our math teachers don't even love that. That's just what I do. X plus 1, 3x plus 1 equals 0. So x equals -1 and -1/3. So those are our critical points. So we need to find f of -1, which is within our domain. Make sure it's within your domain. And we need to find f of -1/3. Oh, positive 1/3. Oh no. This should be negative. Negative. Positive. Positive. See, I gotta practice factoring. Ha 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 ha. Minus. Minus. This is positive. There we go. Positive 1/3. Alright? So, we need to evaluate our function. Not our derivative, our function. So, you're plugging this into Desmos, and you're finding f of -2, which just happens to be -2. You're plugging in and finding f of 2, which happens to be 10. You're plugging in f of -1, which happens to be 1, and you're plugging in a third. Make sure you're using 3 decimals. It comes out to be -0.185. So here is your absolute min, and here is your absolute max. So again, just like what we did on the test, just like what we did last chapter when we were finding absolute maxes and mins, nothing's changed. The only difference is we've given it a cool name, extreme value theorem. All right, so we've got 2 more theorems. Rolle's theorem. Now, Rolle is a guy who made this theorem, and it's fine. We like Rolle's theorem. But really and truly, later on, another guy found mean value theorem, which we're going to do next. Mean value theorem is a little more functional, and it actually works in more cases than Rolle's theorem does. Rolle's theorem is only going to work in one case, whereas mean value theorem is going to work in all the cases. They kind of do the same thing. But let's look at both of them. All right, Rolle's theorem. So if f of x is continuous on a closed interval AB, sound familiar? All of these have started like that. Now we're adding something. And it's differentiable on the open interval from A to B. And, got a little bit more. F of A is equal to f of B. Then there is a point C between A and B such that f prime of C, so the derivative of the function at C, equals 0, which means that you are going to have a horizontal tangent line, or we could say you're going to have a relative max or a relative min. Basically, you're finding a critical point. Now, I do have a picture for this as well. So if f of x is continuous on a closed interval from A to B and differentiable on an open interval from A to B, and f of A equals f of B, then there is a point C in between A and B such that f prime of C equals 0. Meaning you've got to have a relative max or a min in between there, and you have to have a horizontal tangent line. So let's look at a picture. So let's say I tell you that f of A is equal to 3 and f of B is equal to 3. They're both already equal to each other. How do you get from one to the other? I mean, there's a couple different ways. You could do a straight line. I'm going to write it nice and light so you could kind of see it. But if you draw a straight line, that whole thing is horizontal. You have a horizontal tangent line the whole way. So it wouldn't matter where you have point C. You've got a horizontal tangent line the whole time. The more realistic way to get there is to curve like that. And then you have a relative max because there's your horizontal tangent line. The other way you could get there is you could go down. But look at that, another horizontal tangent line. Okay? So, there's just so many ways that you can get there. And even if you go crazy and you go up and down and up and down and up and down and then you get there, well, somewhere in there you've got a relative max or a relative min, And somewhere in there you've got a horizontal tangent line. Now, let's look at this one. I want to show you something. Let's say I tell you that A is equal to 0 and B is equal to 0, but I give you a graph that looks like this. Okay? So nowhere in there do you have f prime of 0, but remember, this is not differentiable right here. You're not differentiable at a corner. So that means that Rolle's theorem does not work. So it has to be differentiable. If it's not differentiable, then it doesn't work. Okay? Now, how do we do this? All right, so Rolle's theorem example. Verify Rolle's theorem for f of x is equal to x squared minus 5x plus 4, going from 1 to 4. Okay, well, the first thing they said is f of a has to be equal to f of b. So that's the first thing we have to find. What's f of 1 equal to, and what's f of 4 equal to? Okay, so again, I go into Desmos and I plug in, or I use my calculator. I plug in a 1, and I end up getting 0. I plug in a 4, and I end up getting 0. So, yay, they're the same. So that means there has to be a critical point in between 1 and 4 where you have a relative max or a min. So let's look. F prime of x is 2x minus 5. If I set that at equal to 0, x is equal to 5 over 2. Now 5 over 2 is between 1 and 4. Okay, and this is where you have a horizontal tangent line. Now, we could draw our picture. We could look at it a little bit here. We've got, there's 1, there's 4. We were at 0 and 0. Now, x squared minus 5x plus 4, that's a parabola going up. So it looks something like this, which means this point right here is at 5 over 2. Okay? Which is about 2.5. So, horizontal, horizontal. All right, so that was Rolle's theorem. Now, mean value theorem. Mean value theorem is where we're going to put all of our eggs in our basket. This is what our homework is going to be on. You're going to be working on this with Mr. Taylor on Friday. Your mean value theorem practice. Okay, so mean value theorem is what we really like. Let's look at what mean value theorem says. Starts off the same. If f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists a point C between a and b such that f prime of C equals f of b minus f of a over b minus a. Now, right now it just kind of looks like letters, but we're going to make it make sense in a minute. So, there's going to exist a point C between a and b such that the derivative, which is the slope of the tangent line, is going to equal this, which is just your formula for slope of a secant line. So, the slope of the tangent line is equal to the slope of the secant line. The instantaneous velocity matches the average velocity. And of course, I'm going to show you a picture so you can visualize it. All right, so we're going to have a curve that kind of looks like this. A is right here, B is right here. And we're going to connect those points. Hopefully I can connect them. Yay! There's our secant line slope. And what this mean value theorem is saying is somewhere in between this A and B on this curve, there is a point where the tangent line, I'm kind of going off a little bit, but the tangent line and the secant line are parallel to each other. Kind of hard to draw that. So the tangent line and the secant line are parallel to each other. Now, let's talk about how Rolle's theorem is kind of the same thing. Look, your slope of your secant line here is just 0. And he said, Rolle said that the slope of your tangent line was also 0. Okay, slope of your secant line is 0, slope of your tangent line is 0. So, great job, Rolle. Great job. But the mean value theorem, and I don't know who came up with it, we'll have to look that up. But the mean value theorem says that it really doesn't matter. It doesn't have to be a slope of 0. It could be any secant slope. Somewhere in between there, there's got to be a tangent line that has that same slope. Slope of the tangent line equals slope of the secant line. Okay? So, how do we do this? How do we do this problem? Okay, well the first thing we've got to do is we've got to find the slope of the secant line. So they gave you 2 and they gave you 4. Now remember, those are both x values. It says use your mean value theorem to show that there is a point between 2 and 4 where the slope of the tangent line is equal to the slope of the secant line. So they gave you the x's. You need to find the y's. So if I plug the 2 into here, f of 2 is equal to 2 squared minus 4 times 2. That's actually going to come out to give me, that's 4 minus 8, so that's negative 4. If I plug in a 4, f of 4 is equal to 4 squared minus 4 times 4. Well, that's 16 minus 16, so that's just 0. So the slope of my secant line is 0 minus a negative 4 over 4 minus a 2. So the slope of my secant line is equal to 2. Okay, slope of the secant line is equal to 2. 2. Find the equation of the slope of the tan. Well, that's just the derivative. Step 3, set them equal and solve. We want to know where the slope of the secant line equals the slope of the tangent line. Where? At what value of x? So we set 2x minus 4 equal to 2. And we find out that x equals 3. Now, it just so happens that 3 has to be in between 2 and 4 for the mean value theorem to actually work, but it should when you do it. If for some reason you get a point that's without or outside of your domain, and then it just doesn't work, meaning we just don't count it. It's not part of our mean value theorem. Our mean value theorem is only going to happen when we've got the things in between. Okay? Now, you should be watching this Thursday evening. This is Thursday evening's homework. So then Friday in class with Mr. Taylor, you guys are going to be working on page 232, and you're going to be doing numbers 1 through 7 odd. So that's page 232, numbers 1 through 7 odd. So not very many problems, but you're going to be working them together, and they're all going to be based on the mean value theorem. We want to make sure that you understand that mean value theorem. Okay? So that's what you're going to be doing Friday in class. All right, you guys have a wonderful day, and I will talk to you later.